So we have a sample here. We have a, kung yung tanaw no, this is a second order. This is a second order ordinary differential equation. And then ingon niya, we are going to use the shooting method to solve this one. So we have d squared t over dx squared plus h prime times t sub a minus t. So by looking at the Leibniz notation, we can say that the t is a dependent variable while dx is our independent variable. So we're going to use shooting method to solve for this one. We have the rod, a 10 meter rod with h, this one, the h prime is 0.01 meter, that is per square meters, or if ato siyang if we raise, ipasaka na to siya sa numerator, that will becomes m raised to negative 2. And we have this one at 20. And the boundary conditions, these are the boundary conditions. When x is 0, our t is 40. And when x is 10, our t is 200. So again, sa itong first method, first step is we're going to convert the ODE system to a system of a first order ODEs. So since this is a second order ODE, we are going to apply this convention. We are going to let z is equal to the first derivative. So that is dt over dx. So aron, pag ato na siyang i-differentiate, this will become a first order ODE, which represents this second order ODE. And if we substitute that to the equation, this equation will become this one. Instead of the second order ODE, we have the first order ODE. dz over dx plus h prime times the quantity t sub a minus t is equal to 0. So take note nga, you can use other variables for this one. Gagamit na tag z rin to represent the first order or the first derivative of this second order ODE. Then we just rewrite it into this form, that dz over dx is equal to this one. And then kaning negative diri murag i-distribute na sa sulod aron hanay siya tan-awon. So we have two equations. You have the z is equal to dt over dx and the other one. Second is guess initial conditions that are not available. So since this is a second order ODE, it means we need two initial guesses. We have already an initial guess of this one, where when x is 0, our t is equals to 40. So unsa man ang atong another initial condition? So ang another initial condition nato is i-relate nato na sa sa katong gi-assume nato. So we are going to relate that sa y prime. Kasi nga naman na siya, di ba? If naatay if we're going to get the f prime x, dapat atong initial condition is natay initial condition nga f of x. If the problem has a second derivative, dapat atong initial condition natay initial condition nga f prime and also the f of x. Ingana na siya. So we have for this specific example, we have an initial condition for this one, but we don't have an initial condition for this one. So it means that we are going to assume the initial condition for that one, which is cz. So muna siya, we just substitute the h and the ta. So kaning h prime na to, and then kaning t sub a is constant. And we just distribute at 0.01, and then the equation is looking like this. So this is our initial condition at x is 0, our t is 40. Now we assume for z, pila man So let's just assume that when z is 10, x and x is 0, t is equal to 40. Let's just assume this one. Solve the initial. So since this is now an IVP, I've converted this into an IVP. We can use these three methods in order to solve the next value. Diba? Kaya naka-first order naman siya ODE. So we can apply Euler's method, the katong predictor corrector, or kaning modified Euler's, and the Runge-Kutta method. So for simplicity, let's use Euler's method with step size h is equal to 2. So again, this is how we get the value of x. So atong x diba is from 0 to 10. And kung atong step size is 2, sa ato pa, and then this is the Euler's method. This is the explicit method, diba? We have the t sub I plus 1 is equal to the old value of t, since the t is our dependent variable. So mo ginato ibutan diri. Plus this one. This represents the slope and the h. So kani siya mo ni siya. This is just the formula. Or z sub I. So anong z sub I? Because kada siya. That represents the slope. The first derivative. And then ato gyapon tagnaon si z sub I plus 1 using the Euler's method. Same formula gyapon. So we just write it there. So for the z, ang iyang derivative is this one. Derivative of the z. Muna siya ang atong equation dira. Step size remains constant at h. Okay, so let's solve the IVP. When I is equal to 0, when this is the first iteration, we have the x at 2. So in here, no, we have x naught is equal to 0. Since our step size is 2, so this will be our x's, no, plus 2, plus 2, plus 2, plus 2, until we reach the 10. So our t1, by initial guess, z is assumed, that is 60. Our z1, we have 10.4. And then afterwards, now we iterate it tanan, and eventually we will arrive that at x is equal to 10, our t is 156.192, and our z is 16.241. So mo na din diba we have a boundary condition. Sige, since ato naman siya na-solve, diba, we're going to check for if the known boundary conditions are satisfied. So sa katong pag-assume nato nga z naught is equal to 10, or kato si dt over dx is equal to 10, ang result, ang t10 nga atong na-solve at when x is equal to 10 is 156.192. And if we compare it with the given boundary, which is known, that is 200. So katong from assume, that is lesser than what we have known from the initial condition or boundary condition. So next is we assume another value of the first derivative, or z naught. Let's say we use 15. So by using 15, by applying again all those steps, we arrive at this result, where at x is equal to 10, that is already at 210.208. So this is much closer than the first assumption when z is equal to 10, or when the first derivative is equal to 10. So we check with this, medyo doon na sila. So this is the first one. This is the first assumption when the z naught, or the first derivative of t with respect to x, is 10. This is the second assumption when z naught is already 15. And then we can find the next value of z naught by using this method of linear interpolation, bisection, and secant to arrive eventually at better approximation for this specific problem.